if you stand, we do. So we're going to do a condensed version of the lesson from 12.2, or at least the, we're going to just go ahead and put it all in one thing. We're going to simplify this thing as much as possible. So if you have some data that is nonlinear, you look at it, it looks exponential, it looks quadratic, it's just not linear. I'm going to show you some steps that you follow in order to make it linear and then analyze the data. So first of all, if you have some data, what you're always going to want to do is first create a scatter. So use that data to create a scatter plot. Second thing you're going to want to do is look at the pattern of the data. And decide which parent function matches the data. More often than not, the parent function you're going to see is an exponential function. So more often than not, we're going to take exponential functions and we are going to turn them into linear functions. We'll transform them using logarithms. Sometimes they're different. Sometimes that's not the case. Sometimes they're quadratic. Sometimes they are a square root function. It depends. But more often than not, you're going to see exponential data that you're going to transform to be linear. So what you're going to do is after you decide which parent function the data looks like, you're going to transform the data by taking the inverse of the response variable, right, or your y value. That should make that data linear. So let's go ahead and do that with a couple different data sets. Our first data set has to do with child mortality rates for children under 5 based on income. So what I've done is I've gone ahead and put this into my TI Inspire calculator. And let's go ahead and look at the graph. So we're going to insert a data and statistics page. And our explanatory variable is income. And our response variable is mortality. So at first glance, this looks like it appears to be looks exponential. Looks like exponential decay. So let's go ahead and transform the data. So what I'll do is I'll call this let's call it trans, and hit enter, and let's define that. Oops, I already have a pre-stored value in there. Sorry about that. So that's going to be equal to. What if we're going to try to transform it using a logarithm? Let's use a natural log. And we're using natural log of our response variable, which we said is mortality. Yes. All right, let's look at the graph of that. So instead of mortality, I'll put trans. And it is still not looking extremely linear. We can tell if it's looking linear or not by analyzing. We'd like to look at the residual. Before we can look at the residual, though, we are going to have to perform least squares regression on this data. Once we've done that, we'll be able to look at a residual plot. And if we look at this residual plot here, it looks like there is definitely a curved shape to this data, which means that the data is non-linear. So we're going to have to try again. Well, if I look at it, so let's go ahead and change this back to mortality. So if I look at this data here, it seems to be that the only other function that it looks like is a rational function, right? If we look at rational functions, in the first quadrant, you'll have a shape that looks a lot like this, and then we would have another accompanying shape in the third quadrant. But we're just worried about this first quadrant. So that's the thing that looks the most like that. So let's go ahead and try to transform this data by expressing it as a rational equation. So let's go mortality. And let's see how that looks. Very nice. And so now we have some linear data, and we can perform, we can analyze least squares regression, the equation of the least squares regression line. And we could do inference on this as well now. All right, so let's look at another data set that has a more common transformation with it. So this person dumped out M&Ms, eats all the ones with the M on top, puts them back in, dumps them out, eats all the ones with the M on top until he has 0 M&Ms left. So let's go ahead and put this data into our TI Inspire calculators. So I have that file loaded up right here. So here we go. We've got course 1, 2, 3, 4, and then below that 5, 6, and the number of M&Ms left. Let's do step 1. Let's create a scatter plot and look at the data. So I want to insert data and statistics. And my explanatory variable is course. My response variable is M&Ms. And this one looks like exponential decay. So let's go ahead and try to transform the data. So let's make another transformation. I'll just do a trans. It's a little easier that way. Let's type. All right, so that's going to be equal to natural log. We'll take the logarithm since we said it was exponential. And let's go ahead and look at the inverse of that. And by the way, in the previous one, you might have said, hey, you didn't transform it using the inverse of a rational function, but it is actually a case that the inverse of a rational function is a rational function. So I did actually take the inverse of it. In this case, if we suspect that it's exponential, the inverse of an exponential function is a logarithmic function. So that's why I'm going to go ahead and take the natural log of my response variable, which is mm. And we get a transformed set of data. And let's see if that is looking linear. Indeed it is, but we should check it by making a residual plot. And it's good to do anyways because first we have to get the least squares regression line, which is good. Uh-oh, something happened. Something is wrong with my domain. If I look down here, I think I know what the problem is. Right here. I'm trying to take natural log of 0. And that's not a thing. So in order to actually perform this, I'm going to have to just delete that data, that piece of data. It's not going to work unless I do that. So let's go ahead and go through the process again. So that's going to be natural log of mm. And now let's see. Yeah, we don't have any undefined values now, right? If I'm trying to make a scatter plot of this thing, and I want to plot some undefined values, it's going to say, no, that's not a thing. We can't plot that. So now we'll be able to go ahead and analyze, create a least squares regression line. There it is. And we will go ahead and look at the residual plot. So, get the residual plot. Nice. That is a good looking residual plot. I don't see any clear pattern in the residual plot, which shows that this data set is indeed linear. So now that we've got a definite nice set of linear data and the least squares regression line, let's go ahead and analyze them. So, we have our predicted value is equal to, so if I'm interpreting this least squares regression line, our predicted value, y hat, is equal to negative 0.680725. That is our slope, right? So what we're saying is that for every increase in course, every 1 unit increase in course, we'll expect our number of M&Ms to decrease by 0.68 M&Ms. Now, if we were going to try to make a prediction on this value, we would actually have to put the data in, right? So we would put our predicted value in for x. We would get a predicted value for y hat, but then we would have to transform the data again by raising it, by taking it e to whatever that data point is value. But this is how you transform nonlinear data so that you can create a least squares regression line. Thanks for watching.